Welcome to the second of a two-video series on functions, math class problems. This video includes problems likely to be in most math courses. I wanted to give you a heads up that the discussions here depend heavily on you having seen the first of the two videos in this series. So if you haven't seen video 1, I recommend going back to that first. The specific topics we're going to look at today: domain and range, implied domain, the vertical line test, the horizontal line test, finding inverse functions, graphical displays of functions, and function operations. Before we can get into this list of 7 topics, it's worth noting that the first 2 of them, involving domain and range, require an understanding of something called interval notation. So before we even begin our 7 topics in this video, we're going to take a quick, about 12-minute diversion into interval and set notation. Interval and set notation. Let's start by imagining a number line, a line that represents all real numbers. And of course, numbers don't end. They go up past the billions and below the negative billions. And so we put the symbols infinity and negative infinity at the end of the number line, not because infinity and negative infinity are numbers, they're not, but because they represent that there's a never-ending list of numbers in both directions. Let's look at an example of a set. Consider all numbers from 3 to 7, represented here. This set would include numbers like 4, 7, pi, 6, or 3. Just to name a few. In set notation, we could express that set this way. The braces at the end of the set are pronounced the set of all, or just the set, and this straight line here is pronounced such that. So this would be read, the set of all x such that x is between 3 and 7 inclusive. In interval notation, we would express the set this way. An interesting fact about interval notation is that it always has a comma in it, and that comma represents the word through. So this would be read the closed interval from 3 to 7. The closed interval, by the way, is one that contains its numerical endpoints, and this one does. Before we go on to many more examples, I'd like to point out that this video is just describing a way that we can talk about pieces of the number line, or sections of the number line, also known as intervals. That we're not solving any math problems here. This is just a vocabulary and a description video. Well, with that in mind, let's continue. Let's consider all numbers between 2 and 9, represented here. It's worth noting that the word between in math excludes, by its very definition, the endpoints. So when we say all numbers between 2 and 9, strangely, we're not including 2, nor are we including 9. This set would include numbers like 7, 2.66, 8.999, 2.001, and just to throw it in there, radical 51, which I believe is about 7 point something. Well, it contains all the numbers between 2 and 9, so how do we describe it? Well, we could call it the set of all x such that x is between 2 and 9, or we could write it as an interval, again with the comma representing the word through, or 2. I would pronounce this the open interval from 2 to 9. An open interval is one that does not contain its numerical endpoints. So when we write this interval, we're talking about all numbers 2 through 9, but not 2 nor 9. Let's consider all numbers that are both above 4 and also 6 or lower, represented here. The set would include 5, 6, 5.312, 4.001, and 4.0000001, just to name a few. In set notation, we could describe this as the set of all x such that x is 4 through 6, including 6. In interval notation, we could describe it this way. Again, I'd like to remind you that the comma represents the word through, so this could be read 4 through 6 or 4 to 6. But I would call it a half-open interval from 4 to 6, including 6. A half-open interval, which I guess could be also called a half-closed interval, but traditionally we don't. A half-open interval includes one of its two numerical endpoints. So, notice the parentheses at the 4 represents that 4 is not a member of this set. The bracket at the 6 represents that 6 is a member of this set. Let's consider all numbers -5 or higher, represented here. This would include numbers like -3, 0, -5 itself, 12, or 13 million and change. In set notation, we would simply write the set of all x such that x is greater than or equal to -5. Interval notation would be expressed this way: -5 through infinity. I would call it a closed interval from -5 to infinity because it includes its numerical endpoint, -5. Let's remember, infinity is not a number. This wouldn't be called a half-open interval. Let's consider all numbers higher than 4, represented here. This would include numbers like 6, 12, a billion, pi plus 7, and 4.00001, for example. We could write it as the set of all x such that x is greater than 4, or in interval notation, 4 through infinity, also known as the open interval from 4 to infinity because it does not include 4 as a member of this set. Let's consider all numbers 2 or lower. This would include 0, -1,000, 1, 2 itself, and negative radical 3, which is about -1.7. We could write this as the set of all x such that x is less than or equal to 2, or in interval notation we would write -infinity through 2, more specifically the closed interval from -infinity to 2, because it includes its numerical endpoint. It's worth noting here for a moment that interval notation is always written in left to right format. -infinity is to the left of 2, obviously, and therefore we write the -infinity first. It would be very strange, and in fact wrong, to call this the interval from 2 through -infinity. How about all real numbers? Every single number on the line. We could call that -infinity through infinity using interval notation. There are other ways to say all real numbers, but we'll leave it at that. Let's consider all numbers that are either 3 or lower or higher than 5, represented here. This set would include numbers like 3, -400, 1,000, 9, or 5.001. In set notation, we could simply write the set of all x such that x is less than or equal to 3 or x is greater than 5. Using interval notation, we have to use a union symbol, which is a mathematical way of representing the joining of two sets into one, as seen here. It looks like the letter U and was inspired probably by that, but it's not technically a U. I would pronounce this the union of the closed interval from negative infinity to 3 and the open interval from 5 to infinity. Let's consider all numbers except 20. Literally every number that isn't 20, represented by this shading here. This includes 47,000, 0, negative a million, 20.0001, and 19.999. Every number that isn't 20. In set notation, we could simply use the not equal to symbol, the set of all x such that x isn't 20. Interval notation requires a union of two sets because these two sets are separated and don't overlap. I would pronounce it the union of the open interval from negative infinity to 20 and the open interval from 20 through infinity. It seems like a strange way of saying all numbers that aren't 20, but we do see this in interval notation, so it's something to be aware of. Let's consider the numbers 2, 4, and all the numbers between 5 and 10, represented here. This includes numbers like 5.001, 9.999, 7, 4 and 2, of course, themselves. In set notation, we'd simply write it out as you would imagine, the set of all x such that x is 2, or x is 4, or x is between 5 and 10. In interval notation, we use braces around the 2 and the 4. Braces around a set are just a way of representing a collection. Notice the comma between the 2 and the 4. That does not mean through, because braces do not make an interval or interval notation. So we're simply joining the numbers 2 and 4 themselves with the open interval from 5 through 10. I would pronounce it the union of the set consisting of 2 and 4 and the open interval from 5 to 10. And now that we're done looking at interval and set notation, let's get back to the main point of this video, which is the topics we'll be looking at. Again, those topics are domain and range, implied domain, vertical line test, horizontal line test, inverse functions, graphic displays, and function operations. Let's consider domain and range as seen from a graphical interpretation. From a previous video, you'll recall that the domain is a collection of all input values in a function, and a range is the collection of all output values. Let's consider this example. Before we consider the domain and range of this function, I'd like to point out some features displayed graphically here in the function. First of all, the open circle. This open circle, when placed on a graph, represents that the function does not contain that point. So this function does not contain the point 3,2. Notice this arrow on the other end of the function. This arrow appears to be pointing upward, but it really has two implications. It not only represents that there are points in this graph that are infinitely high up, in a sense that the function goes up forever in that direction, if you will. But that arrow also implies that there are points that go infinitely far to the left. And while that arrow appears to be pointing more upward than it does leftward, the implication is that there's a in some sense, forever upward and leftward motion to this graph. Now that we've analyzed the features of the symbols in the graph, let's talk about the domain. Now in a minute I'll show you the domain of this function. In other words, what are all the possible input values for this function? But before I can do that, I have to give you a frame of mind here. When answering questions about domain and range, one often has to have a conversation with oneself because there's no math procedure for finding the domain and range of a function displayed graphically. So listen in on my brain as I have this conversation with myself. So, I want the domain of this function, which is the collection of all inputs, or x values. Well, what x values are represented in this graph? Does this function contain a point that has an x value of 3? Well, no, it doesn't, as represented by the open circle. Does this function contain a point whose x value is 4, or 5, or 1,000,000? Well, no to all of those, because there are no points on this graph whose x-coordinates are 4 or 5 or anything higher than that. Does this graph contain a point whose x-coordinate is 2 or 1 or 0 or -1? Well, yes, it contains all those. Does this function contain a point whose x value is -1,000? Well, yes, it does, because of the forever leftward nature implied by the arrow in this graph. So by just considering what are all the possible x values in this graph, it's occurred to me that any x value represented in this shaded green arrow here is a possible input to this function. So in some sense, that shaded arrow represents the domain of this function. In other words, any number in there is a possible input. Well, that shaded region goes from -infinity on the x-axis all the way up to 3, but not including 3. In other words, there's a point on this graph whose x value is 2.999, but there is no point, because of the open circle, on this graph whose x value is 3. And therefore the domain is all numbers from -infinity through 3. And before we go on to range, it's worth pointing out that to answer a domain or range question, there is no mathematical procedure to follow. It's simply the result of a realization. By looking at this picture, I had the realization that all the points on this graph have x values between -infinity up through and not including 3. And that realization led me to the domain that you see there. Now let's continue with this one example and talk about the range. Again, the range is all the possible outputs, or y values, of a function. So I have to have a similar conversation with myself to determine the range. Well, looking at the graph, what are all the possible y values? Does this function contain points whose y values are -1, -2, -3, -4, and -5? Well, yes, it does contain such points. But notice that this function, for example, does not contain points whose y values are -6, -7, or -1,000. There simply aren't any points that low on this graph. Well, does this graph have points whose y values are +1,000 or +1,000,000? Well, it does, because of the arrow. And so when I think about the range, it occurs to me, I have a realization, that any of the y values represented in this shaded green arrow are possible outputs to this function. but that nothing lower than -5 would be a possible output because there are no points there. And so I would say that the range of this function is all numbers from -5 through positive infinity, including the number -5, which you'll see represented by the bracket, because this function actually has a point whose output is -5. By the way, it's the point 1, -5 at the bottom of this graph. Well, I'm done with this example, but I want to leave it up to juxtapose it with a similar example that has some slight different meanings. You'll notice these two examples look roughly the same, but a few things have been changed. Before we answer the domain and range, let's look at some features of this graph. This solid dot here represents that the function does in fact contain the point 32, unlike the previous function. And this arrow here, in conjunction with this dotted line here, which by the way is called an asymptote of a graph, and this video isn't about that specifically, but those two things together represent something slightly different than the arrow did on the first example. They represent that there is an infinite upward progression of this graph, if you think of it that way, but that there is not an infinite leftward progression of this graph, in the sense that the placement of that dotted line or asymptote there represents that there are no points on this graph to the left of that line. With that being said, let's consider the domain. The domain is all possible inputs. So here's this conversation I'll have with myself. Looking at this graph, I can see that all the possible inputs are between -2 and +3, inclusive of 3. In other words, there are no inputs below -2. There simply isn't any graph over there, as implied by the dotted line. And there are clearly no inputs to this function beyond +3 or to the right of 3. So I would express the domain as all numbers -2 through 3, including 3. Why including 3? Because there is a point on this graph whose x-coordinate is 3. Why not including -2? Well, the dotted line implies that there is no point on this graph on that line or to the left of it. Now let's consider the range of this function. The range is the same as the function on the left. This function contains outputs anywhere from and including -5 up to positive infinity. Let's take a look at another example. Let's find the domain and range of this function. First though, let me point out some features. This arrow here on the left side of the function seems to be getting closer and closer to the x-axis. Because it's drawn that way, the assumption here is that this graph goes infinitely far to the left, but never crosses that line. A function would never be drawn so close to the x-axis if that weren't the implication. So that has to have been the author's intent. On the right side here, just a reminder, this upward arrow, so to speak, is an indication of two things. One, that there are infinitely many points going upward on this graph, but that it also goes infinitely far to the right as well. So, with all that in mind, let's first talk about the domain. The domain is all possible inputs to this function. So let me have a conversation with myself here. Does this function have an input value of -1,000? Yes, somewhere far to the left there's a point whose x-coordinate is -1,000. Does this function have an input value of +1,000,000? Yes, somewhere far, far to the right there is a point on this graph whose x-coordinate is 1,000,000. And not only that, but It seems to me by looking at this graph that any x value or input I would choose, there is a point on this graph corresponding to that. In other words, any real number is a possible input to this graph. So I'm going to display my domain as all real numbers, or if I choose interval notation, negative infinity through infinity. Now let's consider the range. The range is all possible outputs. Here's my conversation with myself. Is there a point on this graph whose y-coordinate or output is 1,000 or 1,000,000? Well, yes, because of the forever upward nature of the graph. Is there a point on this graph whose output is negative 1,000,000 or even -1? No. If you look at this graph, there are no negative outputs whatsoever, or y values. Is there a point on this graph whose y-coordinate is 0? No, there isn't. By virtue of the fact that this graph appears to be drawn in such a way that it never touches the x-axis or intersects with it. So there's no point on this graph whose y-coordinate is 0. But wouldn't there be a point on this graph for any number above 0? For example, if I chose 0.0001, wouldn't there be a point on this graph that has that as its y-coordinate? Well, that seems to be the implication by the way it was drawn on the left. So I would say yes to that. And after having this conversation with myself, it occurs to me that any of the y values in this green shaded arrow correspond to an output on this graph. And therefore, I'm going to express the range as all numbers 0 through infinity. Notice I've used an open interval by excluding 0 because there is no point on this graph whose y-coordinate is 0. Just anything above 0. Here's another example. This thing is called a step function for somewhat obvious reasons. Before I figure the domain and range of this function, which I could do simply by the picture, it's worth taking a brief excursion into where a step function would come from. So imagine you had a job where you're being paid for a task, and depending on how long that task took you, you would receive different pays. Instead of paying you hourly in the traditional sense, suppose you're being contracted to do a job, and if it takes under 2 hours, you're going to charge $40. If it takes between 2 and 4, including possibly 2 itself, you're going to charge $80. And if it takes between 4 and 6, you're going to charge $130. That kind of scenario in real life would lead to a step function. Your pay is a function of the amount of hours it takes you to complete the task. Now, I didn't need that information to answer the domain and range, but it was just something worth looking at because step functions do occur in the real world. Back to the question of domain. Domain being all possible inputs, it appears to me just by looking at this graph, if the input is anything between 0 and 6, then there will be an output to this function, and so I'm going to list the domain as all numbers 0 through 6. But notice I've excluded 0 itself and included 6. You'll notice the open circle on the far left side of the graph means that this graph does not contain the point 040. In terms of your job, in terms of that example, if that were part of this, that would mean that you don't get any pay. There's no issue of pay if you work 0 hours. Okay, as far as range goes, range is all possible outputs. There are only 3 possible outputs to this function: 40, 80, and 130. Any other y value than 40, 80, or 130 does not correspond to any points on this graph, and therefore the range is just those 3 numbers. Let's talk about the concept of implied domain. We'll get to that in a moment. First, let's consider the following three functions. Now, these functions appear to be the same, other than the fact that they have different names. One's called j, one's called k, and one's called m. For example, if I asked what j of 12 was, you would probably say 36, because j is the function that multiplies the input by 3. 12 times 3 is 36. Well, likewise, k of 12 is 36, and m of 12 is 36. And this shouldn't be surprising, it's just strange that I've named this function three different things, or so it would appear. Well, the point I'm getting at is that the domain of a function is all the possible inputs, and it would appear just on what's being shown here that any number could be an input to this function. Any number is multipliable by 3. If you were asked the domain of any of these functions, or if I were, I would say all real numbers to all of them if they weren't listed. But that's sort of my perspective as the reader of the function. What if I'm the author of the function? I'm the one creating it. What if in this first function in j of x, I wanted the domain to only have two numbers? For whatever reason. It would be strange, but as the author of the function, I'm allowed to state any domain I like. What if for k I decided the domain would be any integer? An integer, by the way, is basically a positive or negative whole number. Or what if I wanted the domain to be all real numbers, including decimals? Well, I can define the domain as the author of the function to be anything I like. So now that I've changed the domain of these functions, it would appear that they are different functions in some sense. They all involve multiplying the input by 3, but they all contain different points. Now at this point you might be thinking, how did he find these domains? Well, I didn't. I'm stating them. You see, in the previous problems, when we talked about domain, we were the reader of the function. We were being shown a function that was created by someone that wasn't us, and we were asked to find its domain. But I'm putting us in the position here of being the creator of the function. If I want to create three functions, all of which are multiplying by 3, but have different domains for all of them, I can create those. Now, that being said, in this first function, j of 12 is 36, obviously, because 12 times 3 is 36, but k of 12 and m of 12 are also 36, obviously for the same reasons. But now, consider j of x having an input of 5. If 5 is the input for j, what's the output? If you thought 15, you're wrong, because 5 is not a possible input per j because the author of this function didn't allow it. It's undefined or does not exist, which is what the DNE stands for. Why doesn't it exist? Because the only possible inputs to j are 12 or 100. So said the author of j. For k of 5 would be 15, because 5 is an integer and therefore an allowable input. M of 5 would also be 15 because 5 is a real number. Real numbers are basically all positive and negative whole numbers and decimals, very roughly stated. Well, we can see that for j of x, j of 2.1 wouldn't exist. We can't plug in 2.1 to a function where the author's not allowing us to. But notice that k of 2.1 also doesn't exist because the author of k restricted the domain to the integers. 2.1 is not an integer, therefore it can't be an input for k, And for m, 2.1 is a valid input because 2.1 is a real number, and m of 2.1 is 6.3, which by the way is 3 times 2.1. Now, I haven't told you yet what implied domain is. Implied domain is the domain that we are to assume the function has if the author neglects to state it. Here's a more formal definition. In other words, if a function is listed and as a formula and no domain is specified, the implied domain is assumed to be all real numbers that you could plug into that function as an input that would yield or lead to a real output. Now, why would an author of a function neglect to state the domain? Well, it happens quite a bit. And so we have this concept of implied domain. Here's an example. Consider f of x here. If I wanted to, I could say that the domain is only the numbers 1 and 3. As an author of this function, I could say you can only plug 1 or 3 into this function, and whatever output you get is the output, but there are only 2 points on this function. But quite often, we just state a function and we don't state the domain of it, because it's implied that if we don't do so, that any real number that we can plug in and get a real number out is a valid input. Now, unfortunately, there's no procedure for finding the implied domain. One simply has to think to oneself, what numbers could I plug in for x? Can I plug in 1 for x? If I plug in 1, do I get a real answer? Well, yes, if I plug in 1 here, I get radical 6. That's some decimal, but it is a real number. Can I plug in 3 here? Absolutely. Because if I plug in 3, I get radical 4, which is 2, and that's a real number. Well, there's lots of numbers I can plug in, and there's lots of numbers I can't. And so finding the implied domain is really about ultimately finding out what inputs you can have that would lead to a real output. Now, there's no procedure here, but I'm going to share my thoughts that led me to the implied domain here. Watch my thought process as it unfolds. First thing that occurred to me is that the radicand can't be negative. The radicand is the thing under the radical, by the way, so the radicand in this problem is 7 minus x. But that can't work out to a negative number, because then I'll have radical negative, which isn't real. It occurred to me that if x were a number higher than 7, let's say x were 8, or 10, or 1,000,000, that the radicand would be negative, and therefore the result wouldn't be real. And therefore I can't plug in 8, or 10, or 1,000,000, or anything like that, without and still get a real answer. So those numbers must not be in the domain. So it occurs to me that x can't be a number higher than 7 to get a real output. Therefore, there must be no numbers higher than 7 in the domain. It also occurred to me that I can have radical 0, can in fact have radical 0, and I can have radical of a positive number as well. And so if the radicand is 0 or positive, I would have a real output. Well, as long as x is lower than 7, look at the function and imagine x being 1 or 2 or 3. If x is lower than 7, I'm going to get a real output here, because the radicand is going to be positive. If x is 7 itself, I'll get radical 0, which is 0, and that's a real number. And so 7 is also part of the domain. In fact, negative numbers are also part of the domain. Imagine x being negative 1,000,000. Wouldn't I then have radical of positive 1,000,007? That's a real number. So it occurred to me that x can in fact be any number 7 or lower. It just can't be higher than 7. Now notice, I didn't apply a mathematical procedure here. I simply thought through what numbers x could and couldn't be, and I've now come to the conclusion that the domain, or the possible inputs, is the set of all x such that x is less than or equal to 7. By the way, you can also write this, and it's very common to write this using interval notation, which would be negative infinity through 7. Here's another example. Now, there are no radicals here, so we don't have to worry about the radicand being negative, and therefore the function not being real valued. But we do have something else to think about here. we have a denominator. Whenever you have a denominator, you have to worry about x's that will make that denominator 0. So, for example, if x were 5, I recommend pausing the video here and plugging in x equals 5 to this formula. In other words, find g of 5 and hit play when you're ready. What you should have found there when you plugged in 5 for x is you should have gotten 1 over 0. But 1 divided by 0, or anything divided by 0, doesn't exist in the real numbers. And so x can't be 5 as an input to this function because it wouldn't give us a real output. But there's other numbers it can't be too. Let's proceed with my thought process here. So my thinking is if the denominator is 0 for any given x, such as 5, then the function would not have an output. Now it turns out the denominator is 0 not only when x is 5, but also when x is negative 3. And you can see my algebra there. I essentially solved the equation denominator equals 0 to find out what x cannot be, or what inputs are not allowed. Therefore, x cannot be negative 3 or 5. That's my first conclusion. But it also occurs to me, as long as the denominator isn't 0, then the function would have a real output. But wait, how about x equals 4? Look at the top function there. If x is 4, is that an allowable input? Wouldn't that give me 0 over something? Yes, it would, but the denominator wouldn't be 0 in that case, and there's nothing wrong with the numerator being 0, so 4 is definitely part of the domain. In fact, any number that isn't negative 3 or 5 will give me a denominator that's not 0. And therefore, x can be any number other than negative 3 or 5. Now, again, there's no procedure here, just a sequence of thoughts that led me to the conclusion that x can be any number other than 5 or negative 3. So I can state my domain as the set of all x such that x isn't negative 3 and it isn't 5. By the way, this can also be expressed using interval notation. It looks strange, but what I'm essentially saying here is x can be anything negative infinity through negative 3, not including negative 3, or, as represented by the union symbol, any number negative 3 through 5, not including negative 3 or 5, or any number 5 through infinity. And while this may seem strange, it is sort of the traditional way of writing the domain of this function. Either one of those two is fine, though, as far as I'm concerned. Okay, before we go to the next problem, I just want to reiterate something about implied domain. If the author of this function, as originally written, had specified a domain, say they had said x is all numbers 10 or higher, and the author wanted that to be the domain, that would have been fine. That's their prerogative. The implied domain is really just us trying to get into the author's head when they don't state a domain. So any author who wrote this function, we would assume that they meant the domain to be all numbers except negative 3 or 5 because they didn't state a domain at all. This last problem is extremely difficult, and if you're confused by the prior two problems, you may want to just fast forward through this one. But if you're up for a challenge, listen in. Now, this problem contains two things that might cause a certain number not to be a valid input. It contains a denominator, as the last one did, but it also contains a radical, as the previous one did. And really, when it comes down to it in a math class, an implied domain question is going to have a denominator or a radical or both, because those are really the only interesting questions to ask about. If a function doesn't have a denominator and it doesn't have a radical, it really more than likely has an implied domain of all real numbers in almost all cases. It's because it's radicals and division by 0, or radicals of a negative and division by 0 are the two things primarily that make things non-real. Moving on with this very challenging problem, let me share my thought process. My first thought was, well, the radicand can't be negative. But if x is anything lower than 5, look at the denominator and imagine x being 1, 2, or 3, say. If x is anything lower than 5, the radicand is going to be negative, therefore h won't have a real output and those numbers aren't allowed. So x can't be any number lower than 5. How about 5 itself? Well, x could be 5. Look at the original function. If x were 5, we would have radical 0, which is 0, and then 4 minus 0, my denominator would be 4. There's no problem with x being 5 itself, it just can't be lower. But then I also started thinking about the denominator. If the denominator is 0, then the function is not going to have an output. I'm going to recommend pausing the video again and try to answer this question during the pause. What value of x would make that denominator 0? Hit pause and then play when you're ready. If you came up with x being 21 would make that denominator 0, then you have a very clever thought process, and I congratulate you on that. You can see by my work here, if x were 21, the denominator would work out to 0, and therefore x can't be 21. Not because 21 would make the radicand negative, but because it would ultimately make the denominator 0. It also occurred to me that that's the only thing that would make the denominator 0, is if I had a 16 under that radical, aka if x were 21. So, after coming to the conclusion that x can't be 21, but also having prior come to the conclusion that x must be 5 or higher, my overall conclusion is that x can be any number 5 or higher except for 21. So, there's two ways I could write that. I could say that the domain is the set of all x such that x is 5 through 21, not including 21, or higher than 21. I could also write this in interval notation. The first interval to the left of the union sign being 5 through 21, excluding 21 itself, and the second interval to the right of the union sign being all numbers higher than 21. Let's talk about something called the vertical line test. Before we get to what that is, let me remind you that a function is a collection of ordered pairs where no two different ordered pairs have the same input or x value. We saw in previous video 1 of this series, that something like this would not be a function because there are 2 points in it that have the same x value or input, and therefore d is not a function. We also saw that something like this would be a function because if you look at all infinitely many points on this graph or this function, there are no 2 points that have the same x value, and therefore v is a function. We also saw that q would be a function for the same reason, because there are no 2 points that have the same x value. Therefore, q is a function. And lastly, we saw that things like this, w, would not be a function because it does contain 2 points that have the same x value, and therefore it's not a function. In fact, it contains infinitely many occurrences of pairs of points that have the same x value, but it only needs to happen once for something not to be a function. So I haven't mentioned the vertical line test, and I am getting to that, but before we do, I want to show you something that I did on purpose. Notice the highlighted boxes. I intentionally put the of x in some of them and not others. See if you can see why some of these functions include the name of x and others don't. Well, before you look too hard, there's absolutely no reason whatsoever. I did this just as a reminder This has nothing to do with the vertical line test, but just as a reminder, in functions, we sometimes include the of x and sometimes we don't, and it doesn't change anything whether we do or don't. It's just a habit that you kind of have to get used to seeing that it's there sometimes and not others, depending on the author's preference at any given moment. Now, back to the issue. What is the vertical line test? Well, I'm still getting to that, but could I point out something first? We have been given 4 functions graphically here, and we determined by the definition of a function, in other words, using the fact that there can be no repeated x values in a relation, to determine that 2 of these were functions and 2 of them weren't. So what is the vertical line test then? Well, the vertical line test is a visual test to determine whether or not a relation is also a function. But wait a minute. We just determined through the definition of a function, by the repeated x value concept, we just determined which 2 of these were not functions. So why do we need the vertical line test? Whatever that is. Well, you don't. Well, if you don't need it, why am I mentioning it? Well, because you're going to hear about it from textbooks and websites and other professors when you study mathematics, and I just want you to know what they'll mean by that when you hear it later. You technically can live without this and determine whether something is a function or not. So let me share it with you now finally. A vertical line test is something that a professor came up with over a century ago to help their students understand a trick to see whether something was a function or not. So this is the idea that a professor came up with. Here's a vertical line. Watch as it runs across the graph. And the question we ask ourselves is, was there ever a moment, even a brief instant, where that vertical line intersected the function twice or more? And the answer is yes, there was, right here. So, because the vertical line intersects the function in 2 or more points, the conclusion then is that D is not a function. But we knew that anyways, and we don't need a vertical line test to find that out. But it is a visual aid that may or may not help you. Let's proceed. Let's look at Q. I'm going to run this vertical line across the graph of Q, and the question is, will it, at any given moment, will it intersect the graph twice? Well, there was never an instant where that line intersected the graph twice, therefore Q is a function. The same thing happens with V. Watch as I run this vertical line across V, and notice that there's never a moment where it intersects the graph twice or more. And because of that, V is a function. And for W, same question. As I run this vertical line across the graph of W, is there ever an instant at which it intersects W twice or more? And the answer is yes. Notice again, right here, for example. In fact, there are infinitely many places where a vertical line would intersect W twice or more, twice in this case, and therefore W is not a function. So remember, the vertical line test isn't something you need, it's just something you're going to hear about, and it may assist you in determining whether something is a function or not. To summarize, this is what we've already said. And let's move on. Let's talk about the horizontal line test. Horizontal line test is a visual test to determine whether a function is one-to-one. I'll remind you what a one-to-one function is. Let's look at some examples. Function f. The question here is it one-to-one? Well, it's definitely a function because no 2 points on this graph have the same x value. But is it a one-to-one function? In other words, are there 2 points on this graph that have the same y value or output? And if you look long and hard enough, you won't find one. There are no 2 points on this graph that have the same y value. Therefore, this is a one-to-one function. Q. This is the same Q we saw a few minutes ago when looking at the vertical line test. And it definitely is a function because no 2 points have the same x value. But it does have 2 points that have the same y value. And therefore, even though it's a function, it's not a one-to-one function. Let's take a look at function s here. No 2 points have the same y value. Therefore, s is one-to-one. And for h, the question here is, are there 2 points on h that have the same y value? And in fact, there are. In fact, there are infinitely many such pairs, but I only need one to determine that the function is not one-to-one. Okay, so as I said, the horizontal line test is a visual test to determine whether a function is one-to-one. But wait a minute, I just determined which of these functions is one-to-one and which isn't without a horizontal line test. So why do I need it? Well, again, we don't. But you're going to hear about it in other places in mathematics. And so it's a good idea to be aware of the idea even though you can live without it. Now here's the idea. Here's a horizontal line underneath f. I'm going to run this upward through f. And the question is there ever an instant at which this horizontal line intersects the graph of f twice or more? Watch as it runs through. Now there was never an instant in there where that horizontal line intersected the graph twice. By the way, it's worth noting the dotted line here, or the vertical asymptote of f, is not part of the graph of f. It's just a line indicating that f has no points there. So, because the horizontal line ran across the graph and never intersected it twice or more, it is a one-to-one function. Let's look at Q. Was there ever an instant where that line hit Q twice? The answer is yes, right here. And therefore, Q is not a one-to-one function by the horizontal line test. Let's look at S. There was never an instant where that line hit S twice, therefore S is one-to-one. And H, was there ever a moment, could you have paused the video at an instant and had that horizontal line intersect H twice? Yes, there were infinitely many places you could pause the video. Here's one of them. And if a horizontal line hits the function twice or more, then that function is not one-to-one. Here's a summary of everything we just said. Next on our list is finding inverse functions. We talked a little bit about inverse functions in video 1. Let me remind you what an inverse function is. An inverse function is just a function that has reversed ordered pairs from a different function. And so, reminding you of that, let's go through the mechanics of finding an inverse to this function. I'm going to show it to you in 2 steps. First, I'm going to show you the algebra necessary to find an inverse, but then we're going to talk a little bit about what it means and what it is that we've found. First, the algebraic mechanics. Notice that a function can be called g of x or just g. I could rename this function y of x or just y if I wanted to. The name of a function doesn't change its ordered pairs and therefore doesn't change the function. But why would I want to change the name to y? Well, normally I wouldn't change the name of a function. Whatever it was called by the author, that's what I would call it. But in this case, because finding an inverse requires the reversal of the ordered pairs of the function, and since ordered pairs are x and y coordinates traditionally, it's better for my brain to rename the function y, because that reminds me of my x and y coordinates that I'm reversing. So now that I've renamed the function, what you do to find an inverse is you literally switch the letters. Notice, x became y and y became x. And now, I have effectively, just by doing that, I have effectively reversed all the ordered pairs of my function. Now, what you do next is you solve for y, at least y in its current location. And so to solve for y, I decided to cube both sides. That gets rid of my cube root. And to further solve for y, I subtracted 5 from both sides, and I've now isolated or solved for y. I'll reverse it around, not that you have to do that. Now notice what we've done so far. We switched x and y, and we solved for the new y. What does that give me? Well, it gives me the so-called inverse function, g inverse. Remember, this is not pronounced g negative 1, and that negative 1 is not an exponent. It's simply an inverse symbol. So I've found the inverse function. Now, if you're a student and you're taking an exam, and your teacher asks for an inverse function, well, we've just found it. This problem is over. But I always like to think about what problems mean, even though I'm done with the problem. What have I just found? Let's talk briefly about that. Here's my original function g of x. In a minute, I'm going to have you pause the video. I have a question for you to figure on your own. Here's my question. What input would we need in our original function to get an output of 4? In other words, what maps to 4? Hit pause and see if you can find a specific number for x that will make the output be 4. Okay, now that you've hit play, if you chose 59, congratulations. And it turns out an input of 59 will give an output of 4. Now some of you may have gotten this, some of you may not have, but watch anyways and you'll see how an input of 59 led to an output of 4. Well, the cube root of 64 is 4, by the way, because 4 cubed is 64. So, I've just found that given an output of 4, I determined that I would need an input of 59 to get that output. Okay, good enough. Well, remember when I asked you this question and you hit pause, supposedly? I could have used the inverse function to do that. What I would have done is simply plug 4 into the inverse function, because the input of the inverse function is the output of the original function. And by simply plugging 4 into the inverse function, I've essentially answered the same question, that I would need an input of 59 in the original function to get an output of 4 there. And so in some sense, an inverse function is a reversal of the process. Let's consider one more thought before we move on to our next two examples. Notice that g contains the point 59, 4, and that g inverse contains the point 459, thus showing that these two functions really do have a reversal of ordered pairs, which is the original definition of what an inverse function is. Here's another example. Suppose we wanted the inverse of this function. Well, if this function involves multiplying by 3 and subtracting 1, you might think that a reversal of that process might involve a division of 3 and an addition of 1, which it turns out it will. Watch and see. So first, rename the function y. By the way, you don't have to do this. I just find it algebraically easier than dealing with f of x as a symbol. It doesn't make any difference if you rename the function y, but that's what I like to do. And then I literally switch the letters, don't do any math, just reverse the letters, and now solve for the new location of y. To solve for y, I decided to add 1 to both sides, and then divide by 3. And now I have the inverse function of the original function f. By the way, in general, we call one of them f and the other one f inverse, but they're both inverses of each other. It's a sort of a reciprocal relationship. Let's look at one more example. Suppose I wanted the inverse of this function. Same process. Call the function y, that's my style anyways, not mandatory. Switch the letters. And what I did here, in an effort to solve for y, I decided to cross multiply or clear fractions. I multiplied both sides by y minus 3. By the way, a quick algebra note. You could now distribute the x if you wanted to, and there's nothing wrong with that whatsoever. I chose not to. I chose a different way, but that would also have given us the right answer. My thought was, if I want to solve for y, let's not distribute the x. Let's just divide both sides by x. Because by not distributing x and dividing both sides by x, it just seemed a little easier to me. And then to solve for y, I added 3 to both sides. And I now have y, which is, by the reversal of letters previously, my h inverse function. Now let's take a look at functions displayed graphically and the kinds of questions you may be asked about these. Here is a function. Let's call it L. And you may be asked to solve or to figure out a problem such as L of 5. Well, generally speaking, L of 5 means that 5 is your input and you're plugging that in, and most of the time that input would go into a formula or an algebraic problem of some kind. But here we don't have an equation, an algebraic equation for this function. We simply have the graphic display. So how do you answer L of 5, or how do you deal with an input of 5 to find an output when you don't have a formula? Well, it's not too hard to do, because this, after all, means to find the output value corresponding to an input of 5. Here's 5 on the input axis, or the x-axis, and what I usually do is I just look down to the graph, or up in some cases, and then over, and I've got my output value of -3, and that's the answer to L of 5. By the way, there's another way to think of this same problem. You simply notice that this point corresponds to an x value, or an input value of 5, and once you realize, hey, that's the point 5, -3, that's the same as saying L of 5 is -3. Either way, same concept, two different approaches. So suppose we're asked to solve L of x equals 6. Normally when we're asked to solve an equation, we think of an algebra problem where we're trying to isolate x. But in this case, it's a little different. L of x equals 6 means find any input or inputs that yield an output of 6. And so the question now is, what would give us an output of 6? What I like to do is go to 6 on the output axis, or the y-axis, and imagine a horizontal line there and see if that intersects the graph anywhere, which it does, and I can look down to the x-axis and get the inputs that would lead to an output of 6. And now I have my two solutions for x. Same problem, slight different approach. If you're asked for L of x equals 6, and you're trying to solve for x, just find 2 points that have an output of 6, or how many ever there happen to be, in this case 2. And once you realize what those points are that have a y-coordinate of 6, you know the inputs that lead to that output, and that's the same as solving the equation. Here's another one. Suppose we're asked for L of 0. Let's remember, this doesn't mean L times 0. That wouldn't make any sense. This means find the output value of the function L when the input is 0. Well, an input of 0 means that there would be an x-coordinate of 0. And where on a graph is the x-coordinate always 0? And the answer is on the y-axis. That's where the x-coordinate is 0. So this question, L of 0, is equivalent to saying find the y-intercept, if there is one, which in this case there is. Notice the y-intercept is here. Now, depending on the size of your screen, you may or may not be able to see that that's not a whole number. When this happens, the best we can do is estimate. I estimate it to be about 8.7. Don't worry if you're off by a bit. I don't think anyone would ever care. It's kind of question where an estimation is necessary. If we knew an algebraic formula for L, which we don't, but if we did, then we could find the exact y-intercept, or the exact value of L of 0. And here's our last graphical problem. Suppose we're asked to solve the equation L of x equals 0. Now, generally when we think of solving, we think of doing algebra and isolating x. And that's not exactly what we do here. Fundamentally, we are solving an equation. We need to put a number where x is for this to be a true statement. In other words, L of some input has to equal 0. That's the same as saying the output is 0, or the y-coordinate is 0. Where is the y-coordinate always 0? On the x-axis. That's where the y-coordinate is always 0. And so this question of finding inputs that yield an output of 0 is really just the same as finding the x-intercepts of the function, if there are any. And in this case, there are 2. Now again, depending on your screen size, you may not be able to see this, but those are not quite whole numbers. So the best we can do is estimate them. Clearly, the one on the right is 4 point something, but 4 point what, we can't tell exactly. So I estimated the one on the right to be 4.2 and the one on the left to be about negative 6.2. Let's start our last topic in this video called function operations. Here's an example. Suppose we were to define this function. And the question that was asked of us was to find f of 3. Well, of course, that means that the input is 3 and we want to find the output. So what we do is we take the given function f of x, the one you see at the top of the screen, and we replace x with 3. That's precisely what it means for there to be an input of 3 into this function. And once we've replaced x with 3, the only thing left to do is to simplify any mathematics that are simplifiable. In this case, 4 times 3 is 12, 3 plus 7 is 10, and you may recall if you learned about radicals in the past that radical 10 is a decimal, and without going into decimals here, there's nothing we can do to simplify, so that's the result for f of 3. That is the output. Suppose we were given the same function f of x, but this time asked a different question, f of a plus 2. Well, a represents some number here that we don't know or particularly care what it is, but nonetheless, a plus 2 is in the parentheses, and that means that a plus 2 is our input for the function. So we have to take the function, the one you see at the top of the screen, and replace x, each x I should say, with a plus 2. And once you've done that, the only thing left to do is simplify if possible. There are a few minor things that we can do here. I'll let you use your algebra imagination to see what I just did. Basic algebra simplifying. Suppose we were given the same function and asked yet a different question, f of x plus 2. And this isn't very much different than f of a plus 2 that we just finished. It can be a little strange though, because what you're going to do here is, as before, you're going to replace x with our new input to our function, x plus 2. It's no different than the a plus 2 problem, but it seems a little different because the letter x is involved in the original function at the top of the screen, and there's also an x in the input to the question we're doing, so it can seem a little strange. Nonetheless, some basic algebra simplification will get you to your final answer to this problem. And that's the basic part of function operations. Function operations can be a little bit more complicated if there's two functions. And we're going to take these two functions and perform some operations on them both. For example, we'll see what it means to add functions, subtract functions, multiply functions, divide functions, and do something called a composition of functions, which would be these last two. Well, let's look at them one at a time, starting with addition. What does it mean to add two functions together? Well, effectively it means what you think it would mean, where you take the two functions and add them together symbolically. Oftentimes when you're performing function operations, you have to do a little bit of algebra skills here. Take your mind out of functions for a minute and just look at the x squared minus 5x plus 3x plus 2, and notice that that's algebraically simplifiable. This has nothing to do with functions per se, that's just an algebra problem. So it's always proper to simplify your answers, so you have to be able to use basic algebra skills when you're doing function operations with two or more functions. Subtraction means what you think it would mean too. Be careful on the subtraction ones. Notice I've put a parentheses around the second function. That's because to subtract k really means to multiply k by -1 and then add. And therefore, when you distribute the minus sign to k, you get this result, which ultimately simplifies to this using just basic algebra. Let's multiply the functions. Well, it can be done as you think it could be. Just multiply them symbolically together. You don't want to turn this into an algebra review, but you may be familiar with the phrase FOIL or some other means of multiplying polynomials. There's the end result there. And to divide the functions means what you think it would mean, one function divided by another. By the way, as an interesting comment on this one, you can do something called polynomial long division. That was not covered in this lesson, and you may or may not be familiar with it, but I did polynomial long division on scratch paper, and I got this. It's not really the point of this lesson. As a matter of fact, I'm not even sure it was worth my time to do that, because I clearly haven't simplified the function. I've really just written it in another form. So I wouldn't even consider that a valuable answer to this problem. It's not wrong, but it's messy and unnecessary. And so I would probably leave h divided by k as you see it there in the lower left corner. Well, that covers the four basic operations. Let's get to this fifth operation of functions called a composition. That little open circle in the middle is not an O. This is pronounced h composed with k. Sometimes it's written this way and it's pronounced h of k. And what it means is that you're going to use the function k as the input to the function h. Okay, you'll see more what that means as I go through the example. Notice what I've done here is I've rewritten the function h, sort of. Look at these two lines and see if you can see the similarity. Now what I'm going to do here, or what I have done so far I should say, notice that I've replaced the input variable x from the original function h, I've replaced it with big wide open parentheses. Why did I do that? Well, because I'm doing h composed with k, this k function right here is going to be the input into the h function, and so 3x plus 2 goes into both of those slots. That's not the final answer to this problem, but that's precisely what it means to compose two functions. It means to plug one into another. Now sometimes that's all you'll do, but in most cases you'll have some algebra simplification to do. And without turning this into an algebra lesson, I'm just going to show my work. If you'd like to hit pause and really analyze every number in detail, I recommend doing that. Otherwise, just accept that it's an algebra simplification that you are already familiar with if you're at this point in mathematics. So we just did h composed with k. Let's reverse it and take a look at k composed with h. By the way, composition is not a commutative operation, meaning when you switch the order, it's possible to get a different answer. And that's okay, and that's what will happen in this case. These are two separate questions. You'll either be asked to do one or the other, more than likely not both. So, k composed with h. That's my composition. It's sometimes written k of h, and it means I'm going to plug h into k. Notice what I've done here. See the two red arrows. Compare them. I've taken the x, or the input variable, from the function at the top and replaced it with a wide open parentheses here. That's because in my composition I'm going to be plugging h into k, which means this h function here is going to get plugged into the k function as shown there. And now that I've set up my composition, the only thing left to do is a little algebraic simplification. And beyond that, there's nothing else I can do here. And while that does complete these 6 function operation problems I wanted to show you, I am done with them, I wanted to add a few extra thoughts on 4 out of these 6, just to prepare you for work that you may see from a textbook or on a website or from a different professor than me. Let's start with h plus k. Remember where we added the functions together? Sometimes you'll see h plus k of x written this way. This is absolutely no different than just h plus k. Remember, the of x in parentheses is optional in functions. By the way, look at this expression h plus k of x. By no means does that mean h plus k times x. The of x is the input variable, and it's optional. You may see it sometimes, and you may not see it others. I'm simply warning you to not treat this problem any differently, whether there's an x there or not. You may even see it written this way, which effectively means the same thing. Well, it does mean the same thing. One other thing you might see is something like this, h plus k of 7. This does not mean to multiply 7 times h plus k. This means to work out h plus k just like we did, and plug 7 in for x and get a numerical output. I won't actually do the problem here, but that's what that would mean. The same's true for multiplication. You might see it written this way. This does not mean h times k times x. This means h times k, and x is the input variable. It means exactly the same thing as the object to the left of it in the green box, where there is no x. Remember, the of x will appear and disappear at the writer/author's discretion. So you have to be flexible in how you interpret these things. You might also see it written this way. This doesn't mean anything different than the other two. It means the functions multiplied together. If you were to see, let's say, h times k of negative 3, this would mean work out h times k just like we did, and when you're done, substitute in an input of negative 3 and work it out and get a numerical output. Same is true for division. You may see a division problem written this way or this way. If you saw this, you would plug 13 into the quotient. The same is true for composition. You might see it written h composed with k. You might see the of x afterwards. You may not. It wouldn't change a thing whether you did or didn't. Now this one you may see written this way without the composition symbol at all. Keep an eye out for this one. It looks like multiplication, but it's not. When you see a function inside of a function like this, or a function followed by parentheses and another function inside there, that is not a multiplication. That is a composition, so keep your eyes out for that one. If you saw h composed with k of 2, it would mean to do the composition h composed with k just like we did, and then when done, substitute an input of 2, work it out, and get a numerical answer. And that completes the lesson on functions and this series on functions and function operations.